we said that chapter 17, 18, 19 and 20 talk about the carbohydrate metabolism. What we need to know about the metabolism of carbohydrate, or the big picture for this process, that in the catabolism you need to change glucose into an energy. Okay, you need to break down glucose to take energy from it. And in the anabolism process, you need to take some compounds like pyruvate to form glucose, and also you need to take glucose to synthesize or to storage it as glycogen. So this is the idea that we will work on. Glucose, we will take the energy from it in catabolism, and in anabolism we will form glucose from compounds like pyruvate, or we will store glucose as glycogen. Let's begin by the catabolism of carbohydrates. This catabolism of carbohydrates, it includes 3 chapters, chapter 17, 19 and 20. The big target in this catabolism is to gain energy, to gain ATP. And ATP we can gain it through 2 ways. A direct way, we call it substrate level phosphorylation, and through transporters like NADH and FADH2 in the electron transport chain. So in the following chapters we will see how we are going to gain ATP from compounds like glucose. Chapter 17, Glycolysis. In this chapter we are going to see how glucose is going to be break down into pyruvate. Okay, and also I will show you how you can apply the rules that I have said before to understand those pathways in a better way and in a very easy way. So let's begin by this pathway. But before studying it, I need to give you some advices. Each pathway you can deal with it in 4 steps. The first step, deal with the adds. What I mean by adds, those things that you add to the pathway, like the ATP here and the ATP here, like the NADH, the ATP. And those adds, you can remember them very easy by knowing the enzyme that will do this reaction, and I will show you how in the next few minutes. The enzyme names, what is the function? Remember the rules. I said that each enzyme name is from 2 parts. The first part is regarding the compound that the enzyme works on, and the second part is regarding the function of the enzyme. We will see it in a second also. And the third thing that you can deal with in the pathways is the compound name. If you remember the enzyme name, or you know the enzyme function, you will know the compound name very easy. And I will show it to you. And the control point. Here, the control point, I will leave it to you to refer it to the slides, because not all the pathways you are required to know the control points of them, but a few pathways. And I will show you the control point in this pathway. So let's begin by the glycolysis pathway. We will begin by glucose. Okay. Now, how to study this pathway? Very easy. Just start by the first reaction. Here we have a hexokinase. And remember from the rules, I said that kinase is a type of enzyme that will take a phosphate group from ATP or from another compound, and it will give this phosphate group to another compound. So here what will happen? The kinase enzyme will take a phosphate group from this ATP, and it will give it to the glucose. So we will have glucose 6-phosphate. Remember, each enzyme name is not a random name. Enzymes are not named randomly. The enzyme name is from 2 parts. This part is regarding the compound that this enzyme will work on, or sometimes the compound that will be the result of this reaction. And the other part of the enzyme name, this part is regarding the function of the enzyme. So here we have a kinase, and I said that kinase, it will take the ATP, it will take the phosphate group from ATP, and it will give it to another compound. Here you know the kinase, so just by hearing kinase you can remember the function of the enzyme. And by knowing hexo means a 6-carbon compound, and it's referred to glucose, so I think it's easier now. Let's see the second reaction. Glucose 6-phosphate, we have an enzyme called phosphoglucose isomerase. Remember that I said isomerase is an enzyme that will do an isomerization process. It will change the place of the functional group. So we will have glucose here and we'll have fructose here. Okay, we change the place of the functional group. How we know this? Just by remembering that isomerase is a type of enzyme that will change the functional group place. And this first part of the enzyme name, it refers to the compound that it will work on. Phosphoglucose, it's the glucose 6-phosphate, because we added a phosphate group in the first reaction. Okay, the third reaction, we have an enzyme called phosphofructokinase 1. This enzyme, from its name, kinase, it will take a phosphate group from the ATP and it will give it to this compound. So we will have a fructose 1,6-bisphosphate. Remember that Bi, it means 2. Okay, and here this enzyme is the regulatory enzyme in this pathway. You need to read more about it in the slides or in the book. Now we have reached this reaction, the fructose 1,6-bisphosphate, an enzyme called aldolase, and I said in the rules that aldolase is a type of enzyme that will do a cleavage. So here we have a 6-carbon compound. It will be 3 carbon here and 3 carbon here. Now this compound, the DHAP, it can't continue the pathway, so it must be transformed into the G3B. And here we have an enzyme called triose phosphate isomerase. Remember that isomerase is a type of enzyme that will make an isomerization. It will change the place of the functional group. So this compound will be changed into G3B. And from now on to the end of the pathway, each thing we will multiply it by 2. Now here we have done from the first part of the glycolysis. Okay, you remember that glycolysis is 2 phases. The first phase is those reactions that you need ATP. Now the second phase, from here to the end, is the second phase, and here you will produce ATP. Okay, so from now on, the glycer 3 aldehyde phosphate, it will continue the pathway. Here we have an enzyme called G3B dehydrogenase. Remember from the rules, I said that dehydrogenase is a type of enzyme that will take a proton, an H+, from the compound, and it will give it to another compound. So the dehydrogenase enzyme will take an H+ from the G3B and it will give it to the NAD+. Okay, so we will have 2 NADH. But this enzyme can do 2 reactions in one step. Also, it will add a phosphate group to this compound. So the G3B in this step will be 1,3-bisphosphoglycerate. It will lose an H+ to the NAD+, and it will join 2 phosphate groups. Now the 1,3-bisphosphoglycerate is a high energy organic compound. It can produce ATP. We can take the phosphate group from this compound and give it to an ATP. The enzyme that will do this is a phosphoglycerate kinase. Remember that kinase is an enzyme that can take a phosphate group either from ATP, but here we don't have ATP. So it will take the phosphate group from this compound and it will give it to the ATP. And so we will have the first 2 ATP here. Now it will produce a compound named 3-phosphoglycerate. Why? Because we just lose a 1 phosphate. Now here the 3-phosphoglycerate will an enzyme called phosphoglycerate mutase. Remember that mutase is an enzyme that can make an isomerization reaction, and isomerization is the change of the functional group place. So it will be 2-phosphoglycerate. An enzyme called enolase, we said that enolase is an enzyme that will remove the water, so the 2-phosphoglycerate will be phosphoenolopyruvate, and you can connect this enzyme name with this name here, eno, okay? The phosphoenolopyruvate is an organic compound with high energy. It can produce ATP by taking the phosphate group from this enzyme. What is the enzyme type that can take a phosphate group? It's the kinase. So we will have an enzyme name called kinase, pyruvate kinase. Okay, so it will take the phosphate group from this compound and it will give it to the ATP, and we will have the second 2 ATP. And the final end that we have reached is the pyruvate. What I need you to know that each enzyme name is not a random name. That's the big idea that I need you to understand. And if you understand how the enzymes are named, you can just know everything in this pathway by just hearing the enzyme. Okay, if you hear pyruvate kinase, you can know that this enzyme will take a phosphate group from the compound and it will give it to the ADP. Okay, I think it will be more easier, inshallah. Now let's see. Now the pyruvate in the end of the reaction has two two fates, either in the process in the presence of oxygen or in the non-presence of oxygen. We will see them in the second, but I need to focus on the net result of this pathway. The net result of this pathway is 2 ATP and 2 NADH. Okay, now let's see what is the the pyruvate, where it can go. Without oxygen, the pyruvate has two ways. Either it goes to alcoholic fermentation and it will produce ethanol, and this happens in the yeast, or it can go to an anaerobic glycolysis, okay, and it will produce lactate. This reaction is very important. They always love to ask about where it happened. It happened in the red blood cells, and it's the only source of energy. Also, it happened in muscles and in lactobacillus and Clostridium botulism. Those are name of type of bacteria. Okay. Now the other way for the pyruvate is either in the presence of oxygen. If there is oxygen, pyruvate can continue to the citric acid cycle. But before entering the citric acid cycle, it must lose a CO2, and it will bind with a coenzyme A. So the pyruvate will be changed to acetyl-CoA. Okay, in the presence of oxygen, pyruvate can enter the citric acid cycle, but before entering the citric acid cycle, it must be changed into acetyl-CoA. Changing into acetyl-CoA need to go through this reaction. Here we have an enzyme called pyruvate dehydrogenase complex. I will talk about it very briefly. This enzyme is composed of 5 enzymes. Those are the 5 enzymes. Pyruvate dehydrogenase, you can know what is the function of this enzyme. Dehydrogenase, it will take an H plus from the pyruvate and it will give it to the NAD plus. So here we will have NADH. The other 2 enzymes are dihydrolipwyl transacetylase and dihydrolipwyl dehydrogenase. Those enzyme names, they contain this part, lipwyl. Why? Because this enzyme and this enzyme contain lipoic acid. Their function, the first one is transacetylase. Trans means to move. To move what? To move the acetyl. What is the acetyl? This is the acetyl. It's a COCH3. Okay, it's a functional group. The acetyl is a functional group. It's COCH3. So transacetylase, it will move the acetyl group in a special mechanism that I will not talk about it in detail, but just to know that you have 5 enzymes. The first one will take an H plus from the pyruvate, it will give it to another plus. The second and the third one, they will work in the acetyl, they will move it in a special way. You can read it from the book or from the slides. And the last 2 enzymes are pyruvate dehydrogenase kinase and the pyruvate dehydrogenase phosphatase. Those 2 enzymes, they will activate and deactivate the first enzyme. So you can say that the mechanism in a very simple way. The first 3 enzymes here in this complex, they will do a conversion function. They will work, each one of them has a special function. But the 4th and the 5th enzyme, they will control the first enzyme. And this conversion reaction happens in 5 steps. Chapter 19, the citric acid cycle. We said before in chapter 17 that the glucose will be break down into pyruvate, and pyruvate can't enter the citric acid cycle in the presence of oxygen but before converting into the acetyl-CoA. So first pyruvate must be converted into acetyl-CoA. Now the acetyl-CoA will enter the citric acid cycle. This cycle is 8 reactions. 4 of them are oxidative reaction. What we mean by oxidation reaction, it means that we will take a proton from some compounds in this cycle and we will give it to a transporter. So the purpose from this cycle is to produce as much as we can from transporters, because those transporters like NADH and FADH2, they will carry those protons, those electrons to the electron transport chain to produce ATP. Now to begin with this cycle, the acetyl-CoA will react with the oxaloacetate in the presence of an enzyme called citrate synthase. Remember from the rules that synthase is a type of enzyme that can make a new bond without the need of energy. So this enzyme will make a bond between the acetyl-CoA and between the oxaloacetate to produce a compound called citrate. Now the citrate will react with an enzyme called acontiase. This enzyme works in 2 steps. The first step, it will remove a water compound, a water molecule from this compound, and we will have a partial compound. It's called cis-acanthiase. Okay, now this cis-acanthiase, we will add a water molecule to it. It will be called isocitrate. Why we will do this? Because the citrate is an achiral compound, and we need to convert it into a chiral compound called isocitrate, because the chiral compound can make a lot of reactions. Now the isocitrate will be converted into a compound called alpha ketoglutarate by an enzyme called isocitrate dehydrogenase. Remember that dehydrogenase is a type of enzyme that will take a proton, an H plus from this compound, and it will give it to a carrier, to an N plus. So the isocitrate dehydrogenase enzyme will take an H plus from the isocitrate and it will give it to an N plus. And here is the first oxidative reaction in this cycle. Also, this enzyme will take a CO2 compound from the isocitrate and it will move it outside the cycle. So this type of enzyme, they can call it also an oxidative decarboxylation. Why? Because oxidative because it took an H plus from the isocitrate and it will give it to an N plus. Decarboxylation means loss of a CO2, and this enzyme can do those two functions. Now the alpha ketoglutarate, it will be changed into succinyl-CoA by an enzyme called alpha ketoglutarate dehydrogenase complex. Now remember that dehydrogenase, is a type of enzyme that will take an H plus from this compound to an N plus. Okay, and the succinyl also, it's an oxidative decarboxylation process. Because the CO2 because another compound of CO2 will be moved out from this compound. So till now we have lost 2 CO2 from this compound and from this compound. So remember that the oxidative reactions, the first two oxidative reactions, reaction number 3 and reaction number 4, they are called oxidative decarboxylation reactions. Now the succinyl-CoA will be changed into succinate by an enzyme called succinate thiokinase. Also, this enzyme is called succinyl-CoA synthetase. Those are one enzyme. Okay, but this enzyme, it has two names. Now, the reaction here is a little bit complicated. The succinyl-CoA will be changed to succinate by a synthetase. Remember that synthetase is a type of enzyme that will make a new bond between two things. The synthetase, will make a new bond between the GDB and the phosphate group here, okay, to produce the GTP. But I said that the synthetase need energy to make this bond. This energy will come from the coenzyme A. Okay, so the synthetase, this enzyme will make a new bond between what? Between the GDP and the phosphate group. But it needs energy from where? From the coenzyme A. Now we have another enzyme. It's called the nucleoside diphosphate kinase. The kinase enzyme, you remember, is responsible for moving the phosphate group. So this reaction needs two enzymes, the synthetase and the kinase. Okay. Now the succinate will be changed into fumarate by an enzyme called succinate dehydrogenase. You know that dehydrogenase will take an H plus from this compound and give it to this compound. Okay, and we will have the fat H2. The fumarate will be changed into almalate by an enzyme called the fumarase. Okay, nothing special about this enzyme. Just remember, fumarase, fumarate, they are similar little bit. And this reaction need to add the water to it. Now the almalate will be changed into oxaloacetate by an enzyme called malate dehydrogenase. You know that dehydrogenase is a type of enzyme that will take an H plus from the malate and it will give it to an H. Now I will give you another idea that can make you understand those pathways very better. All the pathways, all the catabolism pathways, we will have the dehydrogenase enzymes. Okay, because in those pathways we need to take some things from the compound and to give it to another compound. So you can see dehydrogenase here, okay, and also we saw the dehydrogenase here, okay, and dehydrogenase here. You can notice this in all the catabolism pathways. We need dehydrogenase enzymes. Okay, and in the anabolism we need another type of enzymes. We will talk about them in the next few videos. Now this is the end of the citric acid cycle, but there is something that I need to talk about. It's the net oxidation of you need to distinguish between the net oxidation of pyruvate or the net oxidation of acetyl-CoA. In the exam, if he asks you about the net oxidation of pyruvate, you need to add the one NAD from here. Don't forget that we have an NADH here. So the oxidation of pyruvate, the net oxidation of pyruvate will be 3 CO2 compounds, one of them here and two of them here. 1 GTP, we have it here, and 1 fat H2, we have it here, and we have 4 NADH, 1 before the cycle and 3 in the cycle. But if he asks you about the acetyl-CoA net reaction, you can say that 2 CO2 and 3 NADH and 1 fat H2. Okay, and we have one pathway. It's the glycosylate pathway. It's related to the citric acid cycle. Why? This pathway happen only in the plants and bacteria. The plants and bacteria are able to convert the fat into carbohydrate, but we, the humans and the animals, can't do this. Why? I will say why in the next few minutes. In this pathway, the beginning is the same as the citric acid cycle. The acetyl-CoA will react with the oxaloacetate to form the citrate, and the citrate will be changed into isocitrate. The isocitrate, now here, have two choices: either continue the citric acid cycle or be changed into a compound called glycosylate by an enzyme called isocitrate lyase. Okay, this isocitrate lyase, the bar lyase, means that an enzyme that will make some kind of a cleavage. But here, and we will have two compounds. The important compound is the glycosylate. The glycosylate will be changed into malate by an enzyme called malate synthase. Okay, and the malate will continue the cycle. It will form oxaloacetate. The oxaloacetate here can go into another pathway to form glucose. So here the idea of the glycosylate pathway is to convert the acetyl-CoA into oxaloacetate, which can go in another pathway to form the glucose. Why this pathway happen only in plants and bacteria? Because in the humans we don't have those two enzymes. The isocitrate lyase and the malate synthase are the enzymes that are responsible for making the glycosylate pathway in the plants and in bacteria. So this is the end of chapter 9. Chapter 20, electron transport chain. In this chapter you are going to see how the electrons and how the transporters that we have made in the citric acid cycle are going to transport the electrons that they carry to this chain. Okay, remember the citric acid cycle, the most important purpose for the citric acid cycle is to produce as much as we can from transporters. Those transporters, like NADH and fat H2, will carry the electrons to this chain. Okay, now the electrons will flow through this chain from complex to another by a very simple idea. Each complex, when you go down in this direction, each complex will have a higher potential for reduction. You know that reduction means to gain H+, to gain protons. So this complex have a higher potential than this complex, and this one higher than this one, and etc. till reach the oxygen, the final electron acceptor. Okay, I will give you some hints to understand this chapter. When you hear ubiquinone, remember that ubiquinone is the same as coenzyme Q. They are the same name. Okay, oxidations and reduction. What I mean by oxidations and reduction, I will show it and to you in a second. Oxidations and reduction. Okay, let's say it now. When you go through this direction, like this arrow, each complex, first it will be oxidized, then it will be reduced. Okay, first it will lose its electron. After that, it will take electron from another compound. We will see it in a second. The last thing, the complex name, you can remember it from this rule. The complex name is two parts. The first part is from. The second part is to. What I mean by from and what I mean by to, let's see it now. Okay, See this complex. This is complex 1. The name of it, NADH ubiquinone oxidoreductase, or NADH coenzyme Q oxidoreductase. The name of this enzyme is very simple. The first part is this part. It's the NADH. It's from. What I mean by from? From the place where this complex took the electrons. This complex will take the electrons from NADH. So the first part of its name, it will be NADH. It will be the from, the part that it will take the electrons from it. Now the second part of the complex name is ubiquinone or coenzyme Q. It will be the part that I said it's to. To what? To the place that it will send the electrons. Okay, so it will take electrons from NADH. This is the first part of the name. It will send the electrons to coenzyme Q. It's the second part of the name. So now you can remember the names very easily. You know that complex 1 will take electrons from NADH and it will give them to coenzyme Q. So what its name? Its name NADH ubiquinone or NADH coenzyme Q. Oxidoreductase means that first it will be oxidized. Second, it will be reduced. Okay. First, this complex will lose the electrons that have took from NADH to the coenzyme Q. Second, it will be reduced. It will take electrons from another NADH. Okay. Now the complex 2, let's see its name. Succinate ubiquinone. Why succinate? Because it's the place that this enzyme took its electrons. And why ubiquinone? Because it's the place that the enzyme sent the electrons to. Okay, so it's succinate ubiquinone oxidoreductase. So now you can know how this complex is named. The coenzyme Q now will take the electrons from complex 1, complex 2, and it will send them to complex 3. And why each complex will gain the electron? Because when you go in this direction, I said the reduction potential will be increased. So this complex has a higher reduction potential than coenzyme Q. And see the name of it. It's ubiquinol cytochrome C. Why? Because it will take the electrons from coenzyme Q and it will send them to cytochrome C. Okay, remember that those 4 complexes are in the membrane, and coenzyme Q, cytochrome C are free to move. Those details you can read them from the slide. They are very easy. You can just print this diagram, or you can write it in a paper, and you just can add the information, the other information that I didn't mention. You can take them from the slide and put them in this picture, and it's very easy. Now the cytochrome C will move its electrons to complex 4. So see the name of this complex. It's cytochrome C oxidase, because it will move the electron from cytochrome C to the oxygen. Okay. Now I think this is all about this chapter. There is another thing. It's the Q cycle. I will give you a special video for this cycle. Anabolism of carbohydrates. The anabolism of carbohydrates is included in chapter 18. The idea here, the idea of this chapter, that talk about glycogen, how we are going to break glycogen and how we are going to synthesize glycogen from glucose. Okay. Also, it will talk about the build of glucose from other compounds like pyruvate, the breakdown of glycogen or glycogenolysis. Lysis means that a breakdown. Okay. Now this pathway is very simple. We have only 3 enzymes. The first enzyme is glycogen phosphorylase. This enzyme will take glucose from glycogen from the side. Okay, you remember that glycogen is a very huge compound, like here. Okay, this is glycogen, is a very huge compound. The glycogen phosphorylase can take the glucose from the side of glycogen. Each glucose molecule it will take from glycogen, this enzyme will add a phosphate group to it directly, okay, without the need of ATP. Remember this, because this is a very important difference between the glucose that we took from glycogen and the glucose that we don't take from glycogen. The glucose that we are going to take from glycogen have a phosphate group directly without the need of ATP. Why? Because the glycogen phosphorylase, this enzyme can take a glucose molecule from glycogen and it can add a phosphate group to it. Now the second enzyme is phosphoglucomutase. Remember that mutase is a type of enzyme that can do an isomerization process. Isomerization is to change the place of the functional group. So with the glucose 1-phosphate, it will be glucose 6-phosphate. Now, the glucose 6-phosphate in muscle, it's enough here. But in liver, we need to change it into glucose by using an enzyme called glucose 6-phosphatase. Phosphatase is a type of enzyme that can remove the phosphate group. Okay, so to review this, we have only 3 enzymes: glycogen phosphorylase. From its name, phosphorylase, it will give a phosphate group to the glucose compound that it took from glycogen. This is a very important difference. Why? In this pathway, we can save 1 ATP. Remember that in the glycolysis pathway, when we start from glucose, in the first step, we need an enzyme called hexokinase. The hexokinase, from where it took the phosphate group from ATP. But here we add a phosphate group to the glucose without the need of ATP. This is why we can save 1 ATP. Okay, because the phosphate group is not from ATP here, like in the glycolysis. Okay, I can give you another idea. When you eat a meal, okay, this meal can go directly into your blood, and the glucose in this meal can be directly used. In this way, we need hexokinase. But if you took a meal and you don't need glucose, the glucose in this meal will be stored as glycogen. After a while, you need glucose. Your body is going to use the glycogen storage, and it will take glucose from it. Here, in this case, you need glycogen phosphorylase. And when you use glycogen phosphorylase, when your body uses glycogen phosphorylase, this will save 1 ATP. Okay, they love to ask about this. Now, the last thing also, in the process of glycogenolysis, we need an enzyme called debranching enzyme. This enzyme mechanism is a little bit confused. It will break the 1,6 bonds between the carbon, and it will form a 1,4 bond. Okay, you can ask me why it will form. It's a debranching enzyme. Okay, so how it can break and form? Very simple. Remember that it's break 1,6 and it form 1,4. The glycogen phosphorylase enzyme can't take glucose molecules from the center of the glycogen. This is a glycogen molecule, okay, and in those red points are glucose, okay. The glycogen phosphorylase can only take and can only work on those glucose molecules in the sides. So the debranching enzyme will go and enter to the center of this glycogen. It will break the 1,6 bonds, and it will form a 1,4 bond to help the glycogen phosphorylase to do its function in a very fast and in a very better way. So remember that the debranching enzyme will break 1,6. Why? Because the glycogen phosphorylase can't go inside the glycogen. It needs only to take from the 1,4 from those sides. So the debranching enzyme will break the 1,6 and will form more and more 1,4 sides, so that the glycogen phosphorylase can work on them. Synthesis of glycogen. This pathway is a little bit related with the previous pathway. We said that in the previous pathway we have 3 enzymes, and also here we have 3 enzymes. The first enzyme is phosphoglucomutase. From its name, mutase means that an enzyme that can do an isomerization function. Isomerization means that to change the place of the functional group. So glucose 6-phosphate will be glucose 1-phosphate. Now the glucose 1-phosphate will react with an enzyme called UDP glucose pyrophosphorylase. Let's see this enzyme name. The first part of it is the same as the produced compound, UDP glucose and UDP glucose. The second part is the function, pyrophosphorylase. This enzyme function is to take a phosphate group from here and a phosphate group from here to produce a 2 phosphates that are combined with each other. Now here you need to know that during the anabolism we need energy. So that the energy, the source of the energy to combine UDP with the glucose is the UTP. Now the fate of those 2 phosphates is as follows. They will react with 2 enzymes. The first enzyme is inorganic pyrophosphatase. By adding water to those 2 phosphate groups, we will have a two separate phosphate group. Those 2 separate phosphate groups, one of them will react with the nucleoside phosphorylase kinase. We said that kinase is a type of enzyme that can take a phosphate group and add it to another enzyme. So this type of enzyme will take the phosphate group from ATP and will add it to UDP to produce UTP. Why? Because to make this pathway continuous. Okay? Because we always need UTP, and the source of UTP is to take a phosphate group from ATP. This ATP, from where it comes? It comes from ATP, and the ATP, from where it joins its phosphate group? From this. Okay, so it just like a abbreviation way to keep this pathway continuous. Now the UDP glucose will react with an enzyme called glycogen synthase. This enzyme will cut this compound into two. The UDP will go out and the glucose will be added to the glycogen. Okay, but you need to know a few information about the glycogen synthase. The first information, this enzyme can't take a two glucose molecule and combine them. It needs a primer. What do we mean by a primer? The primer here called glycogen. Okay, this glycogen is a primer that is formed from 8 glucose at least. The first of all, those 8 glucose, they can combine with each other by a special way through special type of bonds. After forming this primer, the glycogen synthase can start its function by taking the glucose from the UDP and add it into glycogen. Also, this enzyme works in a way that is the opposite of a glycogen phosphorylase. And the last thing, in this pathway we need a branching enzyme. Those branching enzymes, they were opposite than the debranching. Here the branching enzyme will form a 1,6 and they will break 1,4. Okay, why they will break 1,4? Because we need to store glycogen. If you leave the 1,4, the glycogen phosphorylase that we said in the previous pathway will come and will break the glycogen. So you need to hide the glucose molecules inside the glycogen by forming a 1,6 bonds. Okay? Gluconeogenesis. It's the synthesis of glucose from pyruvate. In this pathway we will take pyruvate and we will form from it glucose. So it's an anabolism pathway. In this pathway you need to focus on the ads. The ads will be ATP, not ADP. Also you start by a 3 carbon compound, you will end with 6 carbon compound, so you must add some carbons to this compound. And the important thing about this pathway, it's the only pathway that needs 3 places. Okay, this pathway will begin in the mitochondria. After the mitochondria, it will move out to the cytosol. After the cytosol, it will move to the endoplasmic reticulum. So let's begin by it. Pyruvate, the first reaction is by pyruvate carboxylase. Remember from the rules that carboxylase is a type of enzyme that will take a carbon carboxylase is a type of enzyme that can add a CO2 group to the compound. So this pyruvate will be oxaloacetate. Remember that the pyruvate is a 3 carbon and the oxaloacetate is a 4 carbon. And in the anabolism reactions, in anabolism pathway, you always need energy. Okay, so this is why we add ATP here. Now the oxaloacetate will be changed into the phosphoenolpyruvate by an enzyme called phosphoenolpyruvate carboxykinase. You know that carboxy means to add a CO2. Kinase means to take a phosphate group from a compound and to add it to another compound. So the carboxykinase first will add a CO2 to the oxaloacetate and it will be a phosphoenolpyruvate, and also it will take a phosphate group from the GTP and it will add it to the oxaloacetate. So here we will have the phosphoenolpyruvate. Now in this step we will done from the mitochondria, and here we will be in the cytosol. In the cytosol, the phosphoenolpyruvate will go through some reactions. They are a little bit reversed from the glycolysis. You can see that the phosphoenolpyruvate will be changed into 3-phosphoglycerate, and the 3-phosphoglycerate will be changed into 23-bisphosphoglycerate by an enzyme called phosphoglycerate kinase. Kinase means that an enzyme that will take a phosphate group from the ATP and it will add it to this compound. That's why we will have a 2-phosphate in this compound. Now the 1,3-phosphoglycerate will be changed into fructose 1,6-bisphosphate. Okay, by the enzyme name is not mentioned here or in the book, so just know that the 1,3-bisphosphoglycerate will be changed into fructose 1,6-bisphosphate. Now the fructose 1,6-bisphosphate will be changed into fructose 6-phosphate by an enzyme called fructose 1,6-bisphosphatase. Remember that phosphatase is a type of enzyme that will remove a phosphate group. The fructose 6-phosphate will be changed into glucose 6-phosphate. Now the glucose 6-phosphate will be changed into glucose by an enzyme called glucose 6-phosphatase. This step, the last step here, happen only in the endoplasmic reticulum. Now the final net of this pathway, how much ATP we need for this pathway? We need 4 ATP and we need 2 GTP. The Curie cycle, I will not talk about it in much details, I just want to give you the idea that they might ask you here. The Curie cycle, it's a cooperation between the liver and the muscle. Okay, in the muscle you will use glucose because you need to take energy from glucose to move your muscles. Now the glucose will be converted into pyruvate and pyruvate will be converted into lactate. This lactate will go to the blood. In the blood, the lactate will reach the liver. In the liver, the lactate will be converted into pyruvate and the pyruvate will be converted into glucose in the glyconeogenesis. Okay, the pathway that we see before a few seconds. Now, a scientist called Curie, he found that this cooperation can save a 2 ATP. So the net reaction here will be you need only 2 ATP and 2 GTP. Okay, the phosphopentose pathway. It's also called hexose monophosphate shunt and phosphogluconate pathway. Those names are other names for the phosphopentose pathway. This pathway is very huge, so concentrate with me a little bit. First hint that I will give you, pentose here means that we will produce some sugars, okay, some 5-carbon sugars through this pathway. Now, to explain this pathway, I will divide it into 2 parts. The first part, it's the oxidative phase. The second part, we call it non-oxidative or rearrangement reactions. Okay, so we have a pathway called phosphopentose. We will divide it into 2 parts, oxidative and non-oxidative. Now, another hint. This pathway is not for producing energy. We are not dealing with energy and we don't care about energy in this pathway. Okay, so you will not see ATP here or anything. This pathway is very important for 2 purposes. The first one is to produce the NADPH. The second one is to produce those 2 compounds, the glyceraldehyde 3-phosphate and the fructose 6-phosphate. So what is the importance of the phosphopentose pathway is to produce the NADPH, and they always love to ask about the NADPH, where it's produced in the phosphopentose pathway. Now the NADPH is very important for the lipid anabolism. Okay? And the second purpose for this pathway is to produce the glycer 3-phosphate and the fructose 6-phosphate. So let's begin by the first part of this pathway. The glucose, we will begin by glucose. Okay, it's like an anabolism pathway. So you will start by glucose 6-phosphate. It will react with an enzyme called glucose 6-phosphate dehydrogenase. The first part, it's you can see that this enzyme name is very huge, but here the first part of the enzyme, it's just the name of the compound that this enzyme will work on. So glucose 6-phosphate, it's the same as here. Okay, so enzyme names are very simple, don't be afraid from them. Okay, the second part from the enzyme, it's the function, the operation that the enzyme will do. Dehydrogenase, this enzyme will take an H plus from this compound and it will give it to NAD plus. Okay, to produce NADPH. This is the first NADPH that have been produced in this reaction. Now this compound, you don't need to know anything about it, it's not mentioned in the book. And here we will have 6-phosphogluconate. Now this the 6-phosphogluconate, I just skipped this part because it's not mentioned in the book, so it's okay. And now the 6-phosphogluconate will react with an enzyme called a 3-phosphogluconate dehydrogenase. It's the same thing that happened in the first step. We will take an H plus from this compound and we will give it to NADB plus to produce NADPH. Okay, and this enzyme also will do a decarboxylation. Decarboxylation means that to lose a CO2. Okay, so this compound from 6 carbon units, it will be 5 carbon units. It will be a 5 carbon sugar, ribulose. Okay, now to see to review what I have said, I am talking about the first part of the phosphopentose pathway. It's just an oxidative part. We will produce NADPH. We have done it from this part. In the end of this part, we will have a sugar called ribulose 5-phosphate. This sugar, before entering the rearrangement reaction, it have two choices, and it will go either in one of them. Okay, the ribulose 5-phosphate, either it will be converted into xylose 5-phosphate or to ribose 5-phosphate. What will determine the conversion is the enzyme. If ribulose reacts with the ribulose 5-phosphate 3 epimerase, it will be changed into Glycolysis. Xylose is an epimer to ribulose. So remember that. To make the epimer, you need epimerase. Okay? To make the epimer for ribulose, you need an epimerase enzyme. And to make the isomerase for ribulose, you need an isomerase enzyme. Okay? So those two enzyme names are very simple. Just you need to know that xylose is an epimer for ribulose, and to change ribulose into xylose, you need an epimerase enzyme, and also you need to remember that the ribose is an isomer for ribulose, and to change ribulose into ribose, you need an isomerase enzyme. Till now, from right now we are going to begin with the rearrangement reactions. The idea of the rearrangement reactions that this ribulose will be converted into xylose and another ribulose will be converted into ribose. So I will have a lot of xylose and I will have a lot of ribose. Xylose and ribose, they are not useful, a lot of useful for the cell. So the cell will change them into those two compounds, into the fructose 6-phosphate and the glyceride 3-phosphate to produce ATP. Okay, so how the xylose and the ribose are going to be converted to another useful compounds is through something we call rearrangement reactions. The idea of the rearrangement reactions is that I will bring a 2 xylose and 1 ribose, and I will change them into 2 fructose 6-phosphate and 1 G3B. Okay, the total number of carbons here is 15 and the total number of carbons here is 15. So what is the idea of the rearrangement reactions? They are 3 reactions. Those 3 reactions will change a 2 xylose and a 1 ribose into 2 fructose 6-phosphate and 1 G3B. This is the first reaction. It's done by an enzyme called transketolase. This enzyme, you need to know 2 information about them. It's similar to pyruvate decarboxylase. Okay, why? Because it do a same thing as the pyruvate decarboxylase. So the transketolase will take, the function of transketolase is to take 2 carbons and to move them. Okay, 2 carbons and to move them. This is the function of transketolase. It will take 2 carbon from xylose and it will move it to ribose to produce the glyceride 3-phosphate and another sugar. It's called pseudoheptolase 7-phosphate. Okay, so what happened in the first reaction? An enzyme called transketolase took 2 carbon from xylose, give it to ribose. Okay, so this 5 will be 7. It will be pseudoheptolase, and this 5 will be 3. It will be glyceride 3-phosphate. Here we have done from the first reaction. The second reaction, it will be done by an enzyme called transaldolase. This enzyme is similar to aldolase. They love to ask you about what is the enzyme that is similar to transketolase. What is the enzyme is similar to transaldolase? So remember this information. Now the transaldolase enzyme, it will work in those two compounds and those two sugars. It will move 3 carbon units. So remember, it's very important. The transketolase move only 2 carbon units. The transaldolase move 3 carbon units. Now the to give you another hint, the moving is from the bigger to the lower. Okay, so here we have a 7 carbon. We will move 3 carbon from this 7 to the lower one. Okay, so remember, always the moving is from the bigger to the lower. Okay, so the 7 will give 3 to the 3, and the result of this reaction will be fructose 6-phosphate. Okay, this compound is very important to me, so I will take it outside this cycle to glycolysis to produce ATP, and also it will produce erythrose 4-phosphate. Now this erythrose 4-phosphate will react with another xylose. Okay, this xylose came from outside, okay, from wherever. It's not important. The important thing is that after the second reaction, I have produced the fructose 6-phosphate, and this is an important compound, and I will save it. Okay, now I will continue the pathway to produce the other fructose 6-phosphate and the one G3B. Okay, so the erythrose 4-phosphate will react with xylose in the presence of an enzyme called transketolase. This enzyme, I said that it moves 2 units, so this one is wrong. Okay, change it to 2. The bigger, the 5 here, will give 2 to the 4. It will not give, it will give 2. Okay, I mistake here. So the 5 here will give 2 to the erythrose. The result, the 4 will be a 6 carbon compound. It will be fructose 6-phosphate, and the xylose will be 3. It will be glyceride 3-phosphate. So to summarize the rearrangement reaction, the rearrangement reaction is done by 2 enzymes, a transketolase and a transaldolase. The transketolase, first thing, it will take xylose and ribulose, and it will form G3B and C-dehydrogenase. After that, the C-dehydrogenase will react with the transaldolase. 3 carbon from this sugar, it will move to this sugar, and we will have the first fructose 6-phosphate. After that, erythrose will react with xylose in the presence of transketolase. A 2 carbon will move from this one to this one to produce the fructose 6-phosphate and the glyceride 3-phosphate. Okay,